Okay, so we are discussing about Eulerian graph and Hamiltonian graph. So for discussing Eulerian graph, so we define a Euler graph. That means a trail is in a graph G is called Euler trail, or we can say that Euler path if it's include each edge of G exactly once. So in Eulerian graph, we visit each edge exactly once. We cannot visit any edges twice or thrice. So for making closed Euler path, that use each as exactly once. So that we make a circuit known as the Eulerian circuit. So the circuit is sometimes known as the Eulerian line. So Euler line. So these are the definitions as per name. First, we define trail, path. Already we have discussed in previous lecture. So on the basis of these above definition, the previous definitions, we define Eulerian graph. So for defining Eulerian graph, that means we have to start our visiting and visit every as exactly once in the given graph. Any as is left without visiting, that graph is not be a Eulerian graph. So you must remember that means for a graph we can give an example. We have to check that graph is Euler graph or not. So first we make a path. That means that path contain all the edges exactly once in the graph G. Okay. So Eulerian graph that passes an Eulerian circuit. That means a graph which is Euler graph. That means which passes always a Euler circuit. So a graph G which contain a Euler cycle is called the Euler graph. So which contain a Euler circuit. That means Euler cycle or circuit. That means a closed path. That means we start our visiting from vertex V1 and return back to the vertex V1 by visiting all the edges. By visiting all the edges in the graph, given graph, exactly once. So that graph is said to be that will contain a Euler circuit or means Euler cycle. Make a cycle, so that graph is said to be a Euler graph. So we take examples related to Euler graph. That means which graph is Euler or which are not Euler graph examples. So hope you understand the definition. So we take this example. So we have the example. That means we have to show that the given graph is Euler graph or not. Just we draw. That means 4 vertices. So we start our visiting from vertex A. So when you start visiting from vertex A and then back to visit, start your visiting. That means you are here moving to this vertices and reach to the vertex D. But there is no way to visit all the vertices. That means B or C. So we do not talk about the vertices. We say that we visit every edge exactly once. So there is no way to visit this edge. No way to visit this edge B and C. So we visit as BC. That means order pair BC. So that means this graph is not a Euler graph. Okay. So another example, you can consider the example. So that means when you take this example, so that means this having 4 vertices V1, V2, V3 and V4. So can you say that this graph is Eulerian graph or not? That means have a Euler path, trail. So that means anyone? This graph is Euler graph or not? Achal, Ajay. Yes, Ajay. This graph is a Euler graph. That means you have not focused on the definitions. Definition says that which contain a Euler circuit. और Euler circuit कब बनेगा? एक साइकिल बनाएगा. साइकिल मीन्स जहां से हमने स्टार्ट किया चलना, जिस वर्टेक्स से हमने विजिटिंग स्टार्ट करी और रिटर्न बैक टू द सेम वर्टिसेस. That means you start your visiting from vertex V1. That means you have visited this vertex. That means this edge. Then you visited this edge. Then you visited this edge and return back to the vertex V1. So make a cycle. And there are only 4 edges in this graph. We have visited all of 4 edges in our cycle. So that means you can say that the path we have to follow, the path is V1, V2, V3, V4 and return back to the V1. So this is the example that we make a path, that means trail, or make a cycle, or make a circuit. So this is the Euler graph. So this is the Euler graph. Now we discuss next example. Next example means this example. You focus on this example, third one. So this is the example of Eulerian graph or not? So, or if this is not a example of Eulerian graph, why this is not an Eulerian graph? So that means we draw here. We draw the graph again. So just you can understand. This graph having 6 vertices. This graph having 6 vertices. That means basically we can give a name as A, B, C, D, E and F. So we have to check, that means this graph is Eulerian graph or not. So our prime focus is that we have to visit all the edges in the given graph exactly once. So to say that the given graph is Eulerian graph or not. So that means you can choose any of the edge. You can choose any of the edge. That means suppose you select the edge A. That means you start visiting from vertex A. So that means you have to visit this vertex. Then you move to the vertex C. Then you move to the vertex D. Then you move to the vertex E. That means this edge is left without visiting. That means when we visit this way, so where we cannot visit any edge twice. Our definition says we visit every edge exactly once. So when you want to move this side, that means you want to visit this particular edge, so you want to return back to this edge. So this is edge is visited twice, but this is not in the definition of Eulerian graph. So that we cannot visit any edge twice or thrice. We can visit every edge exactly once. So we cannot move to this side. So that means when you cannot move to upper side, so you cannot move to upper side. So this means that you have option. That means you have to visit this edge, then you have to visit this edge. But same problem here. That means some edges are there which are not visited by any person, or that means who are visiting the edges. So that means some edges are left without visiting. So such type of graph is not a example of Euler graph. Now we have to check all the possibilities. We have to check all the possibilities. That means as many as possibilities are available for checking the graph is Eulerian graph or not. So that means the possibilities how to check. That means see this example, same problem. That means if we remove these two edges, if we remove these two edges, that means we remove these two edges. So that means we make a cycle, or that cycle is construct a circuit, or circuit is a Euler graph. Okay, so we start our visiting A, B, C, D, E, F and return back to the vertex A. So we visit every edge exactly once, at least once. Now, next, this is not an example of Euler graph. So we write not an example of Euler graph, because some edges are there we cannot visit in the graph G. So that is not a Euler graph. Okay. So next, we take the next example. This example, that means these two example are the example of Eulerian graph or not. First, you try the given graph is not Eulerian or Eulerian graph. So check this one. That means this graph is Eulerian graph or not. Or this is not Eulerian. Why this is not Eulerian? So we start our visiting. That means when you start your visiting from vertex A, choose the initial vertex as vertex A, and you start working, visiting all the edges exactly once. That means we start visiting and then visit to this edge. Then we need to visit this edge, but we cannot visit the same edge twice. So this no route is not possible. That means for using this route, we cannot say that the given graph is Eulerian graph. Now we have another choice. Another choice means if we take B as an initial vertex. If we take B as an initial vertex, then we say that first we visit this one. First we visit this edge, then 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 we visit this edge. So this is the example of Euler graph. You see that means when we choose B as an initial vertex, then we visit all the vertices. Sorry, all the edges. But when we visit all the edges, these edges make a cycle. Make a cycle, not make a cycle, because that means when what is our path? So we follow path is that we start from B to C, C to D, then B, then after A, then D. So not make a circuit form. This not make a circuit form. So in circuit form, so cover all the definitions which has Euler trail, path, circuit, cycle, then is called a Euler graph. Now you see this example. That means this is a Euler graph or not. This is a Euler graph or not. So in first view, that means so we see this example. That means how to say that this graph is Euler graph or not. That means making a circuit or not. So you start, that means visiting from vertex B. When you start visiting from vertex B, so that means first you visit this edge. Then visit to this edge, then visit to this edge, and visiting all the edges for second, that means this graph, and back to the B, and now again we start visiting from this edge, then visiting this edge, and visiting this edge, and visiting this edge, return back to the same origin vertex. That means make a cycle. When we make a cycle, so here you see that we write in the definition, we visit all the edge exactly once. So visit, that means our restriction on visiting of the edges. That means we visit every edge exactly once, but we have no restriction to vertices. So that means vertices may be repeated. So you remember this, we visit every edge exactly once, but vertex may be repeated in Euler graph. So these are the examples which are related to the Euler graph, and some points you can understand. The connected graph G has an Eulerian trail if and only if it has at most 2 odd vertex. So it has either no vertices of odd degree or exactly 2 vertices of odd degree. So this points will help you to identify the given graph is Euler graph or not on the basis of the degree of the vertices. Degree of the vertices. Second point, so a directed multigraph G has an Eulerian circuit if and only if G is linearly connected and the n degree of each vertex in the graph G is equal to out degree of a graph G. So we will discuss the directed graph after this topic. So then you can understand the topic. That means this second point. So you know about the what is the difference between directed and undirected graph. So undirected graph doesn't have any direction. We can visit V2A, A2B or C2D or D2C. But for directed graph, we have a particular direction. That direction we represented by an arrow. So on the basis of that arrow, we can see that we need from vertex A to B or vertex B to A. Okay, so third point is that if exactly 2 vertices are odd degree, then G has a Euler path but no Euler circuit or Euler cycle. If any graph, that means any graph is given, which graph having 2 vertices of odd degree, so that means that graph cannot make a path, Euler path, so that means also cannot make a Euler cycle or not a Euler circuit. Not a Euler circuit, so that means not a Euler graph. So fourth point is that if all the degrees are even, so then the graph G has both Euler path and Euler circuit. So for this case, you have no need to check further things. That means we see that these two examples will satisfy point 3 and point 4. So point 3 and point 4, so how to satisfy? That means the vertex B and vertex D. The vertex B and vertex D are odd degree vertex. So that means degree of vertex B is 3 and degree of vertex D is equal to 3. So this graph having 2 vertices of odd degree, this graph having two vertices of odd degree, So two vertices of odd degree, that means this cannot make a Euler cycle or Euler path. So we write as this is not a example of Euler graph. So this is not a Euler graph, So this is not a Euler graph, but this graph, second graph, you see that all the vertices of this graph, are even degree, So that means degree of A is 2, degree of B is 4, degree of E is 2, degree of F is 4, and degree of D is 4 and degree of F is 2. So that means second graph having all the vertices of even degree. So that means all the vertices of even degree. So that graph contain a Euler cycle or Euler circuit. That or any graph which contain Euler path or Euler circuit, this is a Euler graph. Okay, so this is about the Euler graph, and next second most important graph is Hamiltonian graph. So Hamiltonian graph, so we define Hamiltonian graph as a simple path that contain all vertices of the graph G. Simple path that contain all the vertices of graph G, where the end point may be distinct is known as the Hamiltonian path. That means we make a simple path, that means start from vertex v1, then we can end at the vertex v4, but cover all the vertices in the graph G. So for example, you can understand the first point as, that means suppose we have this graph. So we have this graph, that means we start from vertex v1, vertex v2, vertex v3 and vertex v4. Now we see that means it contain all vertices of the graph G. So contain all vertices of the graph G. That means we start from vertex v1. Now vertex v1 to vertex v2, vertex v2 to vertex v3 and vertex v3 vertex v4. We stop here. So this construct a simple path. Simple path, that means we visit from v1 to v2, v2 to v3, v3 to v4. That means start and end vertex are different. So here we write same thing. That means where end point may be distinct is known as the Hamiltonian path. So this path is known as the Hamiltonian path. So when this path is known as the Hamiltonian path, now we move to the circuit. So a circuit in a graph G is called a Hamiltonian circuit if it contains each vertex of graph G exactly once. So you can compare with Euler graph or Hamiltonian graph. In Euler graph, we write in the definition, we visit every edge exactly once. But in case of Hamiltonian graph, so in Hamiltonian graph, that means we visit every vertex of the graph Z exactly once. So contain each vertex of graph Z exactly once, except the starting and end vertex. So that means when we make a circuit, so we can start our visiting from vertex V1 and return back to the vertex V1. So we accept this vertex, we visit all the intermediate vertices or median vertices exactly once. So a graph G containing a Hamiltonian circuit is known as the Hamiltonian graph. So that graph make a Hamiltonian circuit is a Hamiltonian graph. So we talk about this example. This is the example of Hamiltonian graph or not? Yes, definitely. Definitely is the example of Hamiltonian graph. So written back to the B1, that means this construct a Hamiltonian circuit. That means we start our visiting from vertex V1, visit all the vertices exactly once and return back to this. So that means we accept this vertex. That means start and end vertex may be same, but all the intermediate vertices visited only exactly once. So this is the example of simple example of Hamiltonian graph. So this is the example of Hamiltonian graph. Okay, so hope you understand. Those who have any problem can ask. So we discuss here some example. So which graph is Hamiltonian, which are not Hamiltonian. So we take a simple example. That means previous example we have shown. We just add one pair of vertices. That means one pair of edges. That means one additional edge in the graph G. So on the basis of that, so we can say that this is the example of Hamiltonian graph or not. Students, first one is the example of Hamiltonian graph or not? Achal, Deepak, Gagan, Gauri, Anjana, Ashna, Ashna. Parveen, Vidhu, we had? Raise hand, students. Otherwise, I remove you from the session. Okay. Okay. So first graph is the example of Hamiltonian graph. So how to say that? That means in Hamiltonian graph we have the definition. Definition is that means we have to visit every vertex exactly once. So this graph having 4 vertices. So 4 vertices, that means we visit all the vertices exactly once and return back to the origin vertex. That will be start visiting from vertex A. So make a cycle, that means A to B, B to C, C to D, and D to A. So make a Hamiltonian cycle. So that means this is the example of Hamiltonian graph. But same question, that means same graph. Question can be asked on the basis of that. That means this graph is Euler graph. This graph is Eulerian graph or not? That means when this is the Hamiltonian graph, but this is Eulerian graph or not? This is Euler graph or not? So our answer is yes, Kumar, no. Okay, very good. So no, because in Euler graph the condition is that means we have to visit every edge exactly once. So every edge exactly once. So we cannot visit this edge. When we want to visit this edge, then other edge will be visited twice or thrice. So, but this is not in the definition of Eulerian graph. That means we visit every edge exactly once. So this is not a example of Euler graph. This is the example of Hamiltonian, but not an example of Euler graph. Same, the move to the second example. So that means for this example, that means try to visiting. That means this is original. That means graph. So having a sorry, one vertex this side in middle. So that in total number of vertices are 5. So A, B, C, D and E. So we have to check the given graph is Hamiltonian graph or not. So we need, that means our purpose to visit all the vertices exactly once. So that means we can start visiting from any source. We can choose any vertex as a source vertex. So that means suppose we start from vertex B, now vertex C, then we move to the E, then A, then D, then return back to the B. But this graph cannot make a cycle. So the graph, we have visited all the vertices, but this vertex is visited twice, you see. So because we have definition, that means we can visit a source vertex, that means start vertex or end vertex more than once, that means twice. Otherwise every intermediate vertex is visited only once. So this is not a example of Hamiltonian graph. Okay, so hope you understand both the graphs and the differences. So we have discussed several examples, that means these are the examples you can try. So that means which example is Hamiltonian graph or which is not a Hamiltonian graph. So try to solve this. That means just you draw, note down the graph and draw, and check whether this is Hamiltonian or not. So which graph is Hamiltonian? That means we need to visit every vertex exactly once. Okay. So suppose we talk about the first one. So that means first one we take as this is initial vertex. So when we visit this side and now visit to this side and this side. So that means this vertex is repeated twice. But in Hamiltonian graph we visit intermediate vertices exactly once. So we cannot choose this path. So where you cannot choose this path. So that means suppose if you are not choosing this path. Uh, you are not choosing this path, that means so you can try, that means you can visit this vertex, then visit this vertex, then visit this vertex, this is also vertex here, then visit to the this vertex. So this is also intermediate vertex. So this is not an example of Hamiltonian graph. So not an example of Hamiltonian graph. But this is the example is Hamiltonian or not. So you, that means taking B as a source vertex. So B as a source vertex, then visit all the vertices, then visit all the vertices and this vertices and move to the this vertices. So this is not a example of Hamiltonian by using this path. That means you can change your path. So when you change the path, so this can make a Hamiltonian graph. So which path we can consider? So that means we have suppose 32 students. So the brain of all the students are working differently. So that means we choose that what a B to C. Someone go for the B to E F. That means we give the name as the name of the vertices. So that means A B C D E and F. So when you start visiting, that means you start visiting from this vertex, source vertex, and visit through this vertex. So this cannot make then this route, then this path. So this is not be the example. Okay. So which route we can try? So that means we visit all the so node. Okay, so not possible. So similarly we can check for the third or fourth. So both are the example of Hamiltonian because make a Hamiltonian cycle. So these are the conditions. That means Euler circuit transfers every as exactly once, but maybe repeated vertices. But in case of Hamiltonian, we visit every vertex exactly once, but is maybe repeated. So you remember first point. For second point, a Hamiltonian graph not contain a self loop. Hamiltonian graph not contain a self loop or the set of parallel edges. That may be any graph which contain which contain self loop or parallel edge, not an example of Hamiltonian graph. So every traversing means visiting every vertex exactly once in Hamiltonian graph. So any self loop or parallel will restrict us to visit every vertex exactly once. So we will repeat twice or thrice. So the self loop and parallels are not the part of the Hamiltonian. Now, third important points that means complete graph. So we already defined complete graph earlier. So K3 that means which having more three vertices and greater than equal to 3 is the example of Hamiltonian. So these are the examples which is also related to the simple example we already discussed in previous case. So these two graphs are very important. I mean, one is Eulerian and second is Hamiltonian. Now, after these two graphs, that means we have covered all the graphs almost. We will discuss some algorithms. We start discussing algorithms. That means which is most powerful algorithm known as the DiscreteMathematics algorithm. So this Discrete's algorithm which will use for the finding the shortest path, which will use for finding the shortest path. So before starting the Discrete's algorithm, we will discuss directed graph. So we have time, so we will discuss directed graph. So for directed graph, so for defining directed graph, that means a graph G yes. Okay. 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 So we will discuss in next lecture. Okay. Thank you, students, for joining the class. You remember all the definitions because all definitions are important. We will relate with other graphs. That means what are the conditions for complete graph, what are the conditions for simple graph, what are the conditions for Hamiltonian graph, then what is the condition for complete graph. So totally you can say that that means maximum part of the graph theory based on the memory. So you just remember all the definitions, then you can understand all related topics and can solve the problems. Okay, so thank you, students. Now leave the session, please. Leave the session, students.